I'm Anik Saha. I, along with my teammate Amimul Ehsan, present SPECTRAL, bidirectional inference of molecule retrieval and spectral generation through contrastive alignment. So first of all, why is this problem important? We often want to identify unknown molecules from a given spectra. Also, getting this spectra for a particular molecule often involves extensive experimental procedure. Therefore, automating this task is of much importance. So first, to formally define our problem, let us consider a library of candidate molecules M1, M2 through Mn. Each molecule has a smile screen molecular graph, an IR and Raman spectrum. For molecule retrieval, our query spectrum will contain IR and Raman spectrum, and for spectral generation, we will have a query molecule M. Our objectives are twofold. First, we have a retrieval objective where we aim to retrieve a candidate molecule that maximizes some similarity score with the spectra. And also we have a prediction objective where we aim to predict spectra whose values are similar to the true spectra values. So although there have been prior works in this field, our spectral differs from those prior works in this major aspect that we want to jointly learn retrieval and spectrum prediction both. And we hypothesize that since these tasks are correlated and they both kind of bridge to different modalities, learning them jointly will basically reinforce each of them from the learning from the other. Now we look at the dataset we use. We use the Raman IR extension of ChemDeal that consists of 282,000 molecules, and we use 80-10-10 training validation and test split. In this table, we present the number of total molecules, the frequency range, and the intensity or activity values. So one thing to particularly note is that the absolute intensity values for Raman spectra are actually substantially higher than that of IR. However, this will not be a problem since we will perform normalization before training and testing. So we need to pre-process this spectra. Why do we need to do this? Well, in our dataset, we actually have discrete point values for different frequency points, and these frequency values for the points are not really consistent across the molecules. Therefore, what we do is we first divide the total spectral frequency range into n equal length bins, and then we, through interpolation, convert all those point observations to a fixed length normalized representation. Now we present an overview of the architecture of SPECTRAL. So first we have a molecule branch where we obtain a molecule structure graph from the smile representation, and we pass that graph through a molecular encoder, recurring encoder, followed by a trainable head which generates a molecule embedding. And we also pass the IR and Raman spectra through a spectra encoder that is trained from scratch to obtain a spectra embedding of the same length. And we then align them contrastively. At the same time, we also predict the spectra values from those molecule embeddings with the MLP prediction head. And we replace those values with the true Bayes spectra values. Here we again summarize what happens with the molecule branch, basically obtaining the molecular embedding, and then the spectrum branch and the prediction head, where we encode the spectra and predict the Bayes spectra values respectively. Here we present our training loss. It has three components. First of all, the lead loss or the contrastive component, then the prediction regression loss, and then a smoothness loss. All of them together combined actually learns the global alignment as well as the local spectral fidelity. At this point, I hand it over to my teammate Amimul. Thank you.
Assalamualaikum. I am Abdullah Muhammad Amimul Ehsan, ID 2005017, row 17 from CT20. Here I'm presenting our spectra. Let me dive directly into our training objective. So as we can see, we actually project our molecular embedding and spectral embedding into a shared latent space, shared embedding space. So we find similarity in that shared embedding space, and after finding that similarity, we'd like to choose which spectra is actually most likely to be the spectra corresponding to our molecule, or which molecule is actually most likely for the spectra. So for query of spectra, we are trying to find out the molecule, and we actually use inference losses in these cases. So we actually considering in both directions, and actually inference loss is something like negative log likelihood of something like softmax. It actually tries to, in the whole area of molecules, it actually tries to which molecular embedding is closer to this spectral embedding, so that we can actually retrieve. And we use actually clip loss for our overall contrastive training. And clip loss is actually a combination of both in our bidirectional inference losses. And we also have a loss for prediction and smoothness. So what are these for? These are for actually our predicting the spectra. So if we go directly into our spectra, we can actually see for each spectra, we have wave numbers ranging from 0 to 4,000, and we divide it into 256 bins. It can be divided into 5 to 100 or whatever other number of bins, but for each bins, we try to predict an intensity, and we draw the graphs like this. So we try to predict for each bins. So for each bins, we predict, and there is a ground root too. So we calculate MSE, mean square error for that. And we also have a smoothness loss. That actually calculates our peak rise drop. If there is a positive directional flow from between two adjacent bins, then it should be in our predicted spectra too. So our predicted spectra becomes shape aware when we use the smoothness loss. So then it actually treats rises and falls much more meaningfully. And our clip was actually aligns our match pairs together, and it actually push apart our negative pairs. So we actually experimented on an RTX 46, and we used three types of frozen backbone molecular encoders. And Camberta only uses SMICE. GraphMP uses SMICE plus 2D geometrical coordinates. Unimoto uses 3D geometry apart from SMICE. And as we can see, Unimoto should perform better as it has more rich information. And we can clearly see that Unimoto outperforms both Camberta and GraphMP, and GraphMP is better than Camberta. And we have a very good performance when we use Unimoto as a backbone. We get more than 90% equivalent one, more than 98% equivalent 5. And as we actually position against prior works, we don't have a unified framework that does both retrieval and prediction, but there are models like variability transfer that does retrieval, or there are molecule to IR or molecule to Raman works that actually does prediction. And as we compare with our state of the arts, and we can clearly see how we much outperform the existing retrieval models. These are the state of the, we beat all the SOTA models. And in case of spectral prediction, we actually perform much comparatively. We have a very comparative prediction similarity, spectral information similarity. And we are actually very robust to limited data. Even if we are trained with 10% of data, we are when we are evaluated against 80% of data, we get more than 50% equal at 5. And when we are trained with 50% of data, we get more than 90% of equal at 5. That's really good. And our data is, and also as we come to on our data, our model is robust to noise, and we perturbated using Gaussian baseline drift, frequency shift, peak drop, scaling, and we can see our model very gracefully handles all the noises and performs considerably well. And here we show ablation. We are actually jointly training for contrastive alignment retrieval and for spectral prediction, but we did an ablation that actually took the molecular embedding and directly use an MLP for spectral prediction. And we can see with the contrastive learning, we perform much better. We are showing here with cosine similarity. So it actually shows a joint training gives more information for meaningful learning. And here we show our case study of molecular retrieval, and we can see the retrieved top molecules are structurally much similar. We can see the same sort of rings, same sort of functional groups, and they are very close. And that means we are actually retrieving chemically very meaningfully. And that comes to spectral prediction. Here we predict for each bean, and we can see we almost address all the peaks, drops, beans, peaks, drops very well. There are slight perturbations in some regions. This is ground truth and this is prediction, and we can see this is very close. There are some false positive or false negative peaks, but the main peaks and main truths are very well handled, and we have a spectral information similarity of 68%. And our challenge, we used simple model NLP for prediction. We used frozen backbones. We could have trained from scratch. Giant training is actually beneficial. We can actually say that. And we can actually evaluate on much multimodal chemistry framework. We just used IR Roman. We could have used UV, NMR, and more other spectrals. And for conclusion here, we can actually conclude that joint training is a giant training encourages the space to retain chemically more meaningful information, and we have a very strong retrieval performance even with limited supervision. And our model actually performs really well in prediction and retrieval.